That's looking good. So, are we all ready?
Already.
Emma will mute and Di will mute immediately after I've said you're live now. Okay.
All right, muted.
Okay, Emma's queued. 12 seconds. And you're live.
Hello and welcome to our last exciting day at VWBPE. This morning, I have the privilege of introducing David Gibson as our next keynote. Dr. David Gibson, Associate Professor of Teaching and Learning and Director of Learning Engagement in Curtin University in Perth, Australia, works as a team thought leader, educational researcher, learning scientist, professor, and innovator. With funding from National Science Foundation, U.S. Department of Education, MacArthur Foundation, EDUCAUSE, and others, Gibson's research focuses on complex systems analysis, design and improvement of cyber learning applications, games and simulations in education, and the use of technology to personalize learning via cognitive modeling, design, and implementation. He is the creator of SimSchool, a classroom flight simulator for preparing educators, and eFolio, an online performance-based assessment system. Everyone, please help me welcome Dr. David Gibson.
Thank you so much for those kind words and great introduction. It's a pleasure to be with everyone today, and I hope to do this as informally as we can when it's in this particular environment. So if you have a question, chat about it. If we need to, we can stop and get into a little bit more depth in an area if you'd like to hear something, and I'll ask Letty to feel free to say, hey, can you hang on a second and back up and talk a little bit more about one thing or another. So diving right in, we're going to talk about some lessons that I've learned recently from doing game-based analysis. This slide with the abstract on it has the key ideas that in measurement today in education, with digital experiences in the forefront, we now have patterns of behavior in time that are high resolution, meaning a lot of data comes through in a hurry. And that high resolution data is about the paths of decision making and action, and these things cluster together in various behavior artifacts. We're going to look at some of these today and talk about the challenges of measuring them and getting some meaning out of them. So the methods that I'm beginning to learn more about are data mining, machine learning, and symbolic regression. I'm going to tell you and show you a little bit about each of those. So the premise is that we now get this highly detailed and time-sensitive documentation, and that gives us clues about the context, the actions, processes, and products of the learner. I have three examples to share with you. The first one is from a project at Harvard. Jody Clark Madura and myself wrote a paper about this. Her colleagues, including Chris Deedy at Harvard, call this virtual performance assessment. In this particular game, the context of the game was children would come to a farm. There was a playground, there was a science lab, there were buildings they could go into, farmers they could talk to, lab tests that they could run. and they were trying to figure out what was wrong with the frogs. The frogs that were being found around the school's pond were misshapen, and they needed to figure out what were the potential causes of that. So the affordance of the game space allowed students to talk, test, walking around, and the processes and products that the students made, they could put things in their backpack, they could get test results, and in the end, they had to make a guess as to what was going on. A second example comes from a massive online course that we put up at Curtin. The context here, we have 3 of them that are running. There's one in astronomy, one in China, Australian trade, and one in participation in the digital age. And in these MOOCs, the typical actions are reading something, controls that are available within a rule process, like in a small simulator, and button presses, and moving around within a meta environment of some kind. And then the processes and products that are made include quizzes, the use of the sim, and some activities. On the screen, you can see what data looks like when it has been run through symbolic regression analysis. The blue line in the lower left-hand corner is the number of activities that were completed by the participants. And all the green dots on top of that blue line are the grades or the final score of people. So if you notice, there's a regime at the beginning, at the far left, that has high scores or a lot of random scores and almost no activities. So these are people who came in, didn't do very many activities, and they exhibit across the entire score range. Then there's a middle regime where that line is going up, and it is a relationship exists between the number of activities that are being participated in and the grade scores, even though there's quite a bit of noise, as you can see the green dots on top and bottom. And then up at the very top, everyone up there has maxed out all the available activities. And you can see the score ranges are a smaller range. I'm just going to double check my sound level here to make sure that I'm not getting too hot. So I'm going to turn it down just a little bit, and hopefully that'll improve things for everyone. Then in the upper right of that screen, we ran a model to look for the equation that would best predict how the scores were operating during that middle regime. And this is one of the reasons that we do symbolic regression analysis. The little red dot that you see in the lower right-hand corner is the choice of the expression, the mathematical expression. The axis in the lower right-hand corner is complexity running up and down, and error running up and down. So as the graph goes from high to low, as you read from left to right, error is being reduced, but complexity is being introduced. So complexity runs from left to right on the bottom, and error runs from bottom to top. And that's true in all of these graphics that you're looking at. So the choice of the equation is on what is called the Pareto curve. That's a place in the complexity of all the equations available that minimizes error without introducing too much complexity. Then the third example, and then we'll go into some depth about how we do these things, is a large retention study that we just completed. The context of this is 52,000 students with over 1,300 variables, and if you want to multiply those two numbers, you'll see how many data elements are in the colorful map that you're looking at. The actions that are taking place in this are both public and private behavioral data actions, some of which is digital, some of which is in the real world. And we're just starting to understand this complexity of data and putting so many different types of data together at this large of a scale about the entire university experience. In this particular example, we created 250 hypotheses, and we tested 50 of them. And I'm going to tell you a little bit more about that. My co-author in this work is Sara de Freitas, who is the Associate Deputy Vice Chancellor of Education at Curtin University, and a host of others. We're working with Deloitte on this particular project. This is an example of how we pulled all the data together. Deloitte did a lot of the field work on this one. Running down the left-hand side of the graphic is about the story of the process. We went out and interviewed people who understand the business processes of higher education. We went out and talked to students. We pulled these pieces together, and this is where the 250 hypotheses came from. The hypotheses were about how all of us at the university, students and staff and administration, how we all view the problem of why do students leave. From that, we then created an environment that we could ask questions about that. The colorful map that you see, the third icon down on the left, is then exploded in the rest of this graph. So in the middle of the graph tells a quick overview of the story. There were 10 basic data sources, and each of these are complex and different from one another, covering about 52,000 students. It represents 300 gigabytes of data, a lot of attributes. Altogether, we're up in the billions of data elements. And from that, using a self-organizing map, we found 8 clusters of behavior. And we're now working with those in a next step. This is what a hypothesis test looks like using the self-organizing map. Notice that the maps on the right keep the outline of the colorful 8 sections on the far left. So we first found the segments, we looked at the statistics involved in the segments, and then we asked hypothesis questions that recolored the map on top of the segmentation. For example, in the upper right-hand corner, you could see what almost looks like a triangle of red. That is where all of the international students, for the most part, they cluster together because they're very much like each other all across their 1,200 and something variables. They tend to cluster together because they share a lot of variables. But note that in that sea of blue that's in the same map, there are international students everywhere. So not all students that are international just sit at the lower corner. Some of them are more like other kinds of students. And this is true for every hypothesis. There are hotspots at various parts of the landscape, depending on how similar the students are in sharing the attributes of the question at hand. This kind of data analysis is exploratory in nature, and I think it's an area that we're all just beginning to learn. I see some people saw that this is Discovery, that is the software that is running this particular analysis. And another closer view, and on that same point again, is that some relationship that we think may hold in a population that's very complex probably only holds in certain circumstances. So looking at the population with a high segmentation lets us better understand those exceptions and where those are taking place, so that we don't make broad sweeping changes in policy or in a new retention activity or an implementation. We can instead get better and better and in micro-targeting. Ultimately, we want to target all the way down to the individual to completely personalize the education experience to help each individual as best as we can to maximize their strengths, their interests, and their aspirations in the university. So now, returning to the big picture, what we just saw in those 3 examples were various kinds of interaction traces. Did someone In the middle school science example, did they talk to the farmer or not? Did they go into the lab? And if they did they run all the tests or only some of them? In the middle example, did someone in the MOOC quit before doing all the activities? And if so, what was their final grade? And in the last one, did a student who did not log into the LMS system, were they dropping out by the third week of school and already in trouble, and so forth? So all the interaction that's available in the virtual worlds, digital worlds, and real world gets pulled together into a big data system. Now, the definition of big data that I like comes from an IBM site, and it's very easy to remember. It comes at us very fast, so it must be dealt with. Big data, you can't analyze it today and then try to do something tomorrow or a month from now or a year from now. You need the information right now in order to make a change that will be useful to you. So typically, big data is streaming in at a very fast clip. It's also quite varied. That means it doesn't line up all that well together. If you have how someone's feeling with how they're academically performing and who their friends are and where they ate lunch, all of a sudden that's quite a varied amount of data. And so how do these things coalesce together? How do they relate even to one another? So that's the second feature of big data. It's highly variable and incommensurable in general. And then there's a lot of it. So it's voluminous. So it's big, and that's where big comes from, obviously, in the title. It has quite a wide variety, and it comes at us very fast. Now, one of the tools that we use in the beginning of the analysis of the middle school science example was to establish what is called ecological rationality. This is simply, where did everyone go on two important questions? Running down the left side of this graph were the predictions that someone made, and later on they made a claim, which is running across. So this is a crosshatch between if you predicted that it was going to be a mutation, then did you also claim later on after you found evidence, did you then also claim that it was a mutation? Well, notice all the numbers and how different they are. So there's, in mutation as an example, 199 people claimed mutation at the end, but if we look at mutation on the prediction side, it was only, well, it was quite a few more actually. Look at that, it's about 600. So a lot of people changed their mind. This is the beginning of understanding how the population shifted from the beginning of the digital experience to the end. There's quite a bit we can do with these numbers in the ecological rationality. They give us an empirical probability of being in one condition or another. And this is done fairly simply by putting the number that exists in the middle of that spreadsheet above either the total line on the bottom or the total line to the far right. And by doing that, we get fractional qualities or probabilities of how the population behaved. Another thing we've been experimenting with, and we're continuing to do this kind of work, is combining various sensor forms. This is an emotive headset that some people may be knowledgeable about. Some work that we were doing at Arizona State University, we put together haptic, eye tracker, wireless galvanic skin response, and the wireless EEG. At Curtin right now, we're experimenting with the Oculus headset and building safety training and other learning contexts, and then studying the relationship that we get from the being able to put someone in an immersive 3D world. So increasingly in games-based research, we'll see these multiple systems giving us a variety of information about the individual learner. This is from research by Helen Chavez and Javier Gomez, who are both at ASU. It's working with them on their team at that time. And this is the data dashboard created there at ASU. The user is in the upper left. You can see her with the headset on. She's performing a task. And as she's performing the task, in the upper right side is an eye tracker showing what part of the screen is she looking at. The larger the dot grows, the longer she's staring at that part of the screen. And during that moment of time, we're watching how affective data is changing and how the EEG data is changing. And we're also seeing what part of the brain is being engaged. This leads us to want to better understand the biometric nets that are taking place. What patterns are occurring? How are those patterns changing over time? How they relate to baseline and resting conditions, and then what happens when we put someone in an experimental activity. These kinds of considerations then lead me to think that we need a new psychometrics. Psychometrics is how we know that someone knows something through a psychological test or measure. So now the new landscape of measurement is quite different, with these more high resolution data streams, big data, and the affordances of virtual worlds and virtual experiences. One of the methods that I think is going to be increasingly important, so we're putting a lot of attention to this, is understanding network analysis. This is one example of that. This data actually came from the ASU study and is showing the relationships taking place in the brain based on the EEG as a network. So we can look at these things and see where active parts of the brain were involved during the task, and can begin to make some inferences about the emotional state, the performance state, and the kind of thinking that was going on during a particular slice of time or an event frame. The network graphs lead to a type of analysis that uses the adjacency table. In the adjacency table, we're looking at every node of the network in that graph that was on the previous page, and its sending and receiving relationship to every other node in the network. This is one of the ways to find what's called centrality in the network. I've pointed out one of those on the graph. If we want to go back here for just a second and take a look at it, it stands out in a couple of ways. Here's AF4 that is receiving 3 signals. AF4, if you're not able to read it on your screen, is in the lower left-hand corner. We can see that it sends out 1 signal and receives 3. But up at the top, we see receiving 2 and sending out 1, 2, 3, 4, 5, 6. So it obviously has a much bigger role in sending than in receiving. And the network analysis on the adjacency table helps us see these relationships. And again, this helps us to bridge the problem of making inferences about how the mind is working during a problem or during a performance. This is another look at symbolic regression. That's some more data, and I just want to point out again one of the features of symbolic regression is that there's not one single answer to the curve that best fits complex data. It's a range of potential solutions. In the lower right-hand corner, again, you can see the table that has error on the vertical and complexity on the horizontal. And that parietal curve is again, has at each point on that curve, the little blue dots, there is an equation. So if I was happy with a high level of error, I could take the simplest possible equation, and it would probably be a linear equation. But if I want a closer and closer fit to the data, I will sacrifice a little bit of complexity and lower the error, getting a better and better fit to the curve. This allows us to really understand and put together complex nonlinear relationships in ways that have been very difficult, if not impossible, to do before now. In typical structural equation modeling, the best we get is we have a hypothesis of the relationships, and we simply get a single correlation number that tells us whether we're on track or not in aligning the variables in the ways we think. Now we can be much more specific about that and can put a mechanical or mechanistic, I should say, explanation on each of the arrows in a network graph. So I'm going to start summing up, and we can get into some questions if you have some. The space that we're talking about now, the virtual space, the game space, the digital, immersive digital space, these are new spaces for performance. These performances obviously unfold in time, and instead of just seeing that time, we now actually have a high-resolution digital record of the evolution of that performance over time. The multivariate spaces of possible actions can be very limited in a simple game, or can be wide, wide open in a social game. And the assets that are used by the learner to solve their problem, to engage in the game, to make something, these can have intangible qualities, or ones that are harder to measure, such as the ones we were measuring with the EEG, and tangible components, things that they're making and doing that they intend. So you might have some unintentional but valuable information that comes along with a learning process, as well as the intentional layer. What did the learner try to do? What were they attempting to get done? The bottom line of this is that all the asset utilization during a digital performance has the potential to provide evidence of what that user knows and can do, particularly if we've arranged the space with that evidence in mind. Wonder if there was a question. I saw a kind of a hand up on that. Letty, can you bring that up again? Thanks.
Somebody had asked if you had already mentioned the name of the software, and I believe it was Viscovery on the live stream.
Thank you. Yes, Viscovery was the software used to make the self-organizing map. The software for symbolic regression is called Eureka. You can also find it, let's see, if you Google Cornell and Eureka, Eureka is spelled odd, it's E-U-R-E-Q-A. Michael Schmidt is the creator of that. It's a very nice piece of work, and I highly recommend that. Network analysis, we've used a variety of tools. I don't have a favorite one now, but we're starting to zero in on Gephi, it's called, G-E-P-H-I. The screen we're looking at now is a tool that comes from Weka, W-E-K-A. Weka is a toolkit for cluster analysis and for machine learning. It's quite powerful, quite easy to use. Most of the work that we want to do in cluster analysis uses qualitative data rather than numerical and continuum-oriented data. It uses things, categorical data, such as apples, oranges, and pears. If you have that within your data system, then the cluster analysis style will be able to utilize those parts of your data to find relationships. This is a screenshot showing a search that I did on the middle school science students, and I was looking to see how the different ways that the students had solved the problem, how their resource utilization changed. One of the things that I noticed in this particular graph was that one group, the small green group, they didn't use very many resources at all, but all of the other groups, almost all of them, used almost all of the affordances. Now, this is a caution to game designers and educational software designers. If we have clear paths that limit the use of resources based on your decisions, then those paths are going to lead to clusters that are more clearly related to your outcomes. Here, all resources were available to all students all the time, and regardless of their conclusion, all students pretty much used all the resources. You can see a few minor differences in these clusters, and those are useful. We found in this particular piece of work that instead of a microscopic tracking level in the data, it was much better to have a small but meaningful, semantically meaningful cluster of actions. So, for example, the programmers at the very beginning of this had open door for every time any door in the entire place got opened. Well, you can guess what that does then. If there are many, many doors all over the place, you need to know, was it the door to the lab, the door to the farmer's house, the door to the store, was it a door on a locker? So it's very important to have contextual information embedded into the click track or into the user trail, so that the cluster analysis can more quickly make sense of the data that's being created. One of the things that can happen with the network analysis is association rules within the network. And this is an example of an association rule that we found in the middle school data. The students who had this specific pattern of use of resources were most likely to show evidence of forming a hypothesis. Notice how much experimentation is going on in this one. So it makes sense that the ones who experimented a lot and went around the circle many times, probably tried an experiment several times, they were much more actively forming a hypothesis of what was going on. And so now we could just pick up from that activity and make an inference about which students were going to have a hypothesis. A few more features of these new performance spaces. They're complex, they have a lot of dimensions to them. We have a mixture of interactivity between the user and the system and their own mental map of what's going on, and the embedded dependencies of the game engine. So if you've set a mousetrap in motion and the next 15 steps was just the game engine doing its thing, then the person has caused the chain of reaction to take place, but they don't have a deep causal connection between their decision and every micro action. So we have to be able to tease out micro level actions that were caused by the engine and macro and meso or middle level and higher level action sequences that are more capable of embedding the intention of the user. The behaviors in these spaces are also nonlinear, meaning that sometimes a very small action can have a huge effect. So we're not generally looking for linear solutions. We're interested in the complexity of a whole system of nonlinear representations that will be a more accurate representation of the dynamics of the spaces that we're looking at. Now, the interesting and very hard bridge to make here is that we know that higher order thinking and creative thinking is going on, and these spaces are definitely supporting that. But as of now, I would have to admit, there is no idea of a pathway from the micro level detail of the data and the higher level semantic meaning of a higher order thought or a creative thought. So there's plenty of work to do still for people interested in getting into this area and exploring what's here. in general, then, I'm saying that the game-based landscape in virtual worlds and in digital spaces, in a sense, lets us try again to get better at understanding what performance assessment really is. Performance assessment is harder than summative multiple choice type assessment. It's harder to observe, harder to make sense of, harder to infer from. But we now have a lot more data and a lot more tools to bring to the table. So we should be able to understand new ways of performing through these new methods of capturing data, analyzing it, and displaying it in new ways. And eventually, we will, I think, get better and better at creating spaces in which higher order thinking is revealed through the decision sequences that people use, and where their physical performances demonstrate skills, such as a pilot flying a plane is now an obvious one that gets done. Here in Perth, Australia, there are many businesses who make millions of dollars helping prepare miners who use huge equipment, and all of that training is done virtually in virtual caves, wraparound spaces, and with a lot of game-based methodologies. And the emotional response, which are increasingly becoming available to be used during the digital experience. You could, for example, be tuned in to when someone is getting frustrated and dial down the stress and dial down the frustration so that they can calm down and think straight and that kind of thing. So we're going to see much more fluid use of these tool sets as a whole to help people understand and learn and perform better. This slide shows, and some people here probably have seen this one before, it was one of the big ahas for me, that we were looking at the thinking stage in the ASU project, and the only time during a fairly long period of time here where the person had a thought, a very short thought, was at a moment when there was a rise in uncertainty and in interest simultaneously. It's the only time when the blue line and the yellow line rose at the same time. So their uncertainty and their interest was peaked. Notice what's dropping, the purple line around agreement and, oddly enough, concentration. So while thinking, we are losing a bit of our perceptual concentration in order to have the energy to think. And we think that is a pretty interesting little signature that, and I think these kinds of signatures are going to start showing up in data analyses of digital games and simulations. I'm going to skip over that one slide because I think all the audience here knows about games, and this slideshow will be available to everyone, I'm sure, and I'll be happy to make it available. But just to conclude and bring all the ideas back together, the methods that I've shown in this talk include data mining, machine learning, and model building. They use, in general, a notion of complexity in which we can form a theoretical foundation for dealing with these challenges that are present today in the digital learning world. The challenges specifically of evolution of performance over time, so there's time sensitivity, relationships of what's used in the spaces, and here I mean by spatial relationships, not just the 3D version of space. This is the use of resources in the virtual space. The multiple layers of aggregations of both the space and time at different scales, and all of that being driven by the dynamics and mechanics of an ongoing game or a complex problem in this behavior space. I appreciate your time and attention today, and I'd be glad to take some questions if you'd like to ask anything or engage on any of the points that I've raised today. I'd be happy to talk with you more. Thank you, Agile Bill. Thank you, Lori Van and Shmera. Thank you.
David, we have a question from the live stream.
Great.
It says, have you looked at the performance of specific subgroups of students, e.g. those on the autism spectrum?
I have not looked at autism spectrum. In fact, one of the things we'd like to do fairly soon, though, is there's a group here in Perth who I think has autism spectrum students who they believe can make really good game producers and programmers. So we'd like to get engaged with them and actually have them work for us. I have not done a study of any kind on that, but I can certainly see where that would be a valuable comparison group using a lot of these methods that we've just been looking at. So I'd be glad to help you think through that or to share further with you if you'd like to try to develop a research idea about that. I'd be very happy to help.
And then I believe a question popped up on the chat by Agile. How can we best follow your future work in this area?
I'm at Curtin University, and you can look at Curtin Teaching and Learning. We're working to establish a games lab and a research lab there, and so I'll be here for a while working on these things, and would welcome visitors as well as collaborators from anywhere. We're looking at 4 big research themes in a center that we'd like to establish: multimodal learning, the leadership and policy issues such as ethics, and about this kind of data, because when you get big data, it can quickly run into ethical issues. Modeling learners, and then modeling the process of learning. So you might call it learning design or pedagogic design. These 4 broad areas, we're hoping to have researchers from across the arts and sciences, learning sciences, neuroscience, even business logistics. I mean, there'll be so many areas that have a bearing on the kinds of things that we can do now in the digital world.
Okay, another couple of questions popped up on the chat. The big issue is, how do we do high order thinking assessment in virtual world simulations? I believe that's what it means by VWS. So if you could answer that.
I would recommend to everyone to take a look at a method of building complex assessments called evidence-centered design. It's by Robert Mislevy and Russell Allman and Steinberg. Came out of ETS's work in the US. I am continually inspired by the body of work that has risen in relationship to that. And the way they would say it is, you have to start with a very good idea of the domain and how you model the domain. So now let me just bring it down to real practicalities here. Let's take a very simple domain, riding a bicycle. Okay, that we know the domain of the bicycle. It's got wheels and pedals, and you have to balance the thing. You have to be up on the seat, at least in the standard model of a bike. So there's a phase of doing domain modeling. Then that leads to the affordances that are available in the digital space you're planning. So if I'm going to have a digital space and I want to test riding and making decisions while riding, I have to put these 2 things together. So in the higher order area, such as leadership, collaboration, creativity, there's a really instructive piece of work being done now at PISA. The PISA test is an OECD project. It will be live in 2015. And the design of that test is now becoming available, so you can read how they've done it. It uses evidence-centered design at its heart, and it's going to measure problem solving and collaboration at the same time, 2 higher order areas. Problem solving has been on their agenda for a while. They're now going to make some scenarios in which the people you're collaborating with are agents. So they're going to be computational agents playing the role of collaborators. And your responses to them, you see how very much game-like this is beginning to be. And here is a major international assessment that will compare kids across several countries on these 2 dimensions using a game-style approach that has been designed with evidence-centered design.
Okay, and then we had another question come up. What did you learn from examining the effect of reward on the micro scale versus the abstract promise of reward at game end?
Yeah, that's really interesting. I don't know if I've got a great comment on that one, but I'll tell you what else it reminds me of is if you take something like the badge projects that are going on now, the Open Badge Infrastructure, or OBI, if you put badges internally in a game, we know that people are motivated by that and will collect them and bring them together. Some people, not all, but some people are extrinsically motivated to collect. And then the collection makes the pathway toward the goal more transparent. It lets you have micro steps along the way, and for all the right reasons. It's not just having objects, it's also opening up assessment and letting assessment be clear. But now here's, I think, related to your question. If you get, let's say, 102 badges along the road of some game and they're only useful inside that game, then what do you do with that? You're done. The game's over. You've learned what you're going to learn, and you have 102 badges in your pocket. So there's the external validity problem of assessment, I think, kind of comes into this. Now, on your specific question, I think it's a great one, by the way, of trying to figure out the differences. I think maybe the same mechanic might hold between the micro level taking place inside a digital interaction, where the more feedback that I have during the event and the more guidance I get, then the better I'm going to be at performing that. But then when I have to transfer that out to a new situation, if those things are not immediately transferable, in other words, if I have to make a leap of some kind, then it's a fault line in the in the external validity of my experience, and it makes transfer harder. I'm just guessing that your question is related to the problem of task transfer, task and skill transfer.
And I believe one final thing was somebody asked for a citation in local chat, and somebody posted a link on there. Did you have any others to share? Oh, there's another question as well. But first that, do you have any other citations that you can share in local chat?
I don't have those available right now, but I think if you just simply Google evidence-centered design, you'll find everything on that piece. If there was a particular topic that I've talked about that you don't get a good Google response to, then I'll be happy to help out. And let me put, one thing I can put in chat is my email, and that way people can get a hold of me.
Thank you, David. And then while you're doing that, another question came up. It says, as someone who has taken several MOOCs and dropped out of most, usually because one, its title did not match up with what I thought its content was to be, and two, I got enough out of some of the content that I needed. I think any useful data would come from simply eliminating me from the data. Is there not a common case for dropping a good chunk of input before doing any meaningful analysis?
Absolutely. That's a fantastic insight. On that slide that I shared with you, we did not look at either of the two ends of the spectrum. So I did not look at those people who did very few activities and scored all over the map. I only looked at the little hill climbers who actually were improving their score via their participation in activity. I also did not really look at in depth the people who already had maxed out all activity and still had a variety in their score. So I chopped the data at both ends because I was looking for the relationship that would tell me, for people who learned from the activities, what was most salient. So I was trying to focus in on that. So I think it's a very good point that you raise. And in MOOCs, we know huge numbers just are shopping around, and others are just coming into taste. So we're never going to have, in most MOOCs, unless we have a true gamified MOOC all the way through that is literally a fun game to be in, I think those completion rates for the typical MOOC are going to stay as low as they are now, because literally speaking, most of those MOOCs are just the same old, same old. We haven't really turned the corner on user interactivity yet in the MOOC space. I think it probably will come, but it won't look like a MOOC at all. It'll just be a game, I think.
Thank you very much, David. I believe those are all the questions we have, and we are almost out of time. Thank you very much for joining us this morning. Everyone, please help me thank Dr. David Gibson for keynoting this morning at VWBPE. Thank you so much.
Thanks. It was great to be with you, and I appreciate the opportunity to speak with you all. And I look forward to staying in touch with anyone that's interested.
And we're all there.
Okay, excellent. That was great, David.